Hello programmers. Today in this tutorial we're going to be talking a little bit about slightly more advanced topics, and I'm going to talk about just a variety of different things, mostly having to do with Codegen Code in Coder's Basilisk. And the way I want to start explaining this is by first here having this, using this itty bitty little program here, which just runs some, has a single Codegen Code in it, right? There's no includes. This is the entire compilation unit. If we run it, you can see that it tokenizes it, it parses it, and then it prints this, right? And it does it before Codegen main finishes executing, right? So this is a good example of just, compile time code doing something, right? Now, in general, Codegen Code can do basically anything that target code can, right? Although what it's limited in doing in terms of touching the outside world is limited by the set of built-in functions. This here is built-in put string, right, which just prints to the console, it prints to the command line, to the terminal, right? So here is the complete list of built-in functions here. Built-in emit, open O file, close O file, read file, get AST, consume. This is one of the functions related to the parser. Get, this is going to get a string, I believe. Built-in gets. Yeah, see, it reads from standard in. So this is a way you can read from standard in if you want to do that. Then there's built-in puts, where I showed you that. Peek is another function related to the parser. This peeks the next token. It gives you a token to a pointer. Get next. Actually, what is the difference between get next and peek, right? Here's get next, right? I actually don't remember. The thing is, it's been a while, right? Okay, right. But what does peek do? Oh, it get next gets the pointer to the pointer, and then peek gives you okay, I see. So next is the variable that holds the pointer to the next token, and then get next gets the pointer to the next variable. I see, right. So that's what that does. I actually didn't remember. I do believe you need that in order to be able to set the parser's state, right? You need to be able to set the value of the next variable, because that's what the parser actually uses. Built-in exit, this just exits the compilation, right? So I can do built-in exit. I believe it takes an argument. I don't remember. Let's see if this works the way that I remember it to. Yes, it does. Okay, see, and now Codegen main executed successfully never happens, right? So this line never prints, so it just, obviously we can make it a number. And then there's built-in stirred up. This is just the stirred up function forwarded over. malloc, this should be obvious. Get argv and get argc. Okay, so basically, I'll show you. This is ctoke.c. Saved argc and saved argv here, right, are available when the main function is called, right, which, by the way, here's where main is, and this just forwards to ctoke_main, right? In fact, I should probably return this here, but I don't particularly care about that, right? ctoke_main gets called here, and then it saves argc and argv here, and then saved argc and saved argv are referenced here, which should be, I don't know, right? Somehow these things are pre-declared somewhere, right, so that they can be accessed. I don't remember where. But all you really need to be able to know. I was hoping I could find where these were pre-declared for this compilation unit. But basically, all you need to know is that compile time code can access the command line arguments. In fact, let's do that, right? Use the key for I equals 0, I is less than built-in get argc. What's it called? We're going to print the command line arguments one by one. Say to argc, where is built-in get argc. I plus plus char pointer arg equals built-in get argv. And we need parentheses for this. Built-in functions parse a little bit differently than normal functions. If they take no arguments, you still need to include parentheses. Of I believe, I should do it, right? What type does it return? Okay, takes 0 arguments. U8 pointer 2. Yeah, okay, right. So it should this should be right. Okay, this should print out the arguments. Oh, hold on. What's? Oh, the idiot. Right. So you see here now we can type A B C D E F G H I J K L M O P. And here's the command line arguments, cbass, main.cbass, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? So we can access the command line arguments from Codegen Code. I can also notably here, let's just define a function here, some function, int A equals 1 plus 2. Now we're going to define a parse hook. QQQ, we're just going to call it QQQ. And what we're going to do is we're going to I'm just going to show you how the parse hook works, right? I'm going to stick it right here. Oh, hold on. Oh, I forgot to declare this code again. Here we go. Here we go. We do tokenization. We enter parsing. Parse hook called right here. So the parse hook gets called right here. We can do it a couple more times. We can also do it here, here. We can obviously do it here. Expression statement requires a semicolon, right? Oh, it doesn't allow that there. Okay, I thought it would allow that there. Column 22, where is this? Interesting, so it does not allow it here. I thought it would. Okay, there. So you're not allowed to put it there. Okay, so I had forgotten where I allowed it, right? So basically here we are generating some, we're calling a parse hook, by the way. I might modify the language so that I allow QQQ right here, right? It kind of bothers me that I don't allow it right here, right? But basically here we are using the parse hook, and then we're calling parse hook several times here, right? This is how the parse hook works, right? This is the technology used for all of C Coder's Basilisk's metaprogramming, right? Okay, let's go through more of the built-in functions, though. I already showed you get RC, get RV. Free should be obvious. Realloc should be obvious. Type get size, right? So type get size will get the size of a type. I think it has, yeah, it has one argument. It returns a U64. arg1 type is a U8 pointer. And it takes in a type pointer, right? So if you, so what this is it's basically a helper function to access, I believe it's in data.c. Is it in data.h? Yeah, this function here. What it is it's just a way to access this function here, which gets the size of a type. If you pass in a type struct, pointer to a type struct, to okay, where were we? To this to built-in type get size, then it'll give you the size of that type, right? It's just a way to access one of the compiler's built-in functions. There's also struct metadata, right? And what this is basically a helper function for getting the size of various structs used by the compiler, right? And the reason that this is important is in the standard node library, right? Hold on, we don't want to. We actually don't want to we want to v-split this. If you go all the way to the bottom, right? I have this function called struct size test that just compares different. I've declared aliases of the compiler's built-in types, and in Coder's Basilisk, and then I compare them with the struct metadata, and this is basically like a little test for the Codegen library, right? So that's why that exists. Hold on, we need to go back to here. Scroll down. Struct metadata, that's that, right? It just gets the size of types like this. Oh, hold on. This struct right here. This is the one used by the AST executor, right? The interpreter that runs Codegen Code. This is the this is one of those things, right? This is the statement struct. This is part of the AST. So basically, the Coder's Basilisk needs to have a version of this inside of Coder's Basilisk. And what I need to do is I need to be able to check and make sure that this thing is the same size as the one in Coder's Basilisk, just to make sure that they are that the implementation is perfect. Validate function. I believe this is something that you basically never really use, right? Validate function here is a here, right? Validate function here. What this does is it takes a freshly parsed function, right? A complete complete AST for an entire function, and then does all the stuff to it to first of all make sure that everything is valid, and second of all to insert constructor and destructor calls, and I believe it also does some type system shenanigans to insert some implied casts. Like for instance, anytime that you have a variable and you read its value, it is implicitly cast to its own type, which is basically a hint to the code generator that it should generate an R value conversion, right? It should dereference the pointer to the variable. If it's a variable in memory, obviously, right? If it's a register, then you don't have to do that. But that's I did that for ease of code generation, right? There is also a function optimizer. I actually don't remember what this does, right? Yeah, it's not important, right? I don't remember what optimize function does, but it does that apparently. I think it might be the thing that packs, that creates executable functions. Yes, and because this function can be called from parsehook, we do end up doing some shenanigans right here. Yeah, but anyway, that's not important. That's not important. What all you need to know is you can call this function of the parser. You can call the code validator from compile time code. The next thing is memcopy. You don't need to explain that. Memset. Then we have various type to string and string to type conversion functions. You should be familiar with these as a C programmer. Peek is fname. Okay, so what this does is it checks if the next token is an identifier, which is a function's name. This one is something which accepts a string and then sees if the string is a function name. This pushes a statement onto the scope currently being parsed. All right, so you can manually add AST nodes to a function being built. This right here, this is a function I realized today is actually kind of not necessary, since you can directly get the AST. Right here you can get the AST. But basically what this does is it gets a pointer to a symbol, right? If a symbol is defined, this will retrieve its pointer. This right here, and by the way, I believe this actually requires that the symbol be defined, right? So retrieve, right? So if, oh yes, it returns null if the symbol does not exist, right? It requires that the symbol be complete if it's defined, right? If it's incomplete, then it is, then it can't be accessed through built-in retrieve sim pointer. Yeah, but basically this is kind of like a faster version of being able to retrieve symbols from the AST. It's just meant to be, kind of easy to use. And obviously, if the symbol does not have if a symbol is defined, right, but it does not have a pre-initializer, then it gives it one. So there's that, right? If it's not incomplete. But that's that. I know I probably shouldn't be going super in depth with these, since you just need to know that these exist, right? Stir_ll dupe. This duplicates a stir_ll. This is a token. This is the struct for a token in the tokenizer. Dupe_ll. This duplicates a linked list of tokens. Parse global. Okay, so what this does, right? Let me show you. This is part of the magic of metaprogramming. Is that what this does is it calls parse global, which is part of the parser. Right here. So it's basically allows you to define data statements, structs, functions, methods. You can do these weird kind of macro op things. These are actually these are manipulations of the compilation state. Hold on, let me scroll through here. What is this? This is compile unit. Oh yeah, this has a lot of the duplicate code from parse global, right? I could technically, I think, just replace parse global with with repeated calls of parse global, but I decided not to do it that way. Parse global is its own thing. So this thing, this parses one global symbol. This right here. And this allows you to call it, right? So what this allows you to do is in Coder's Basilisk, you can actually parse a global symbol, right? Here, right? So for instance, I could let's do function codegen part. Right, that should work, I believe. Yeah, it's parse underscore global. So let me do that. We're gonna quickly and we're gonna define a struct in the middle of a function, right? And this should work. I haven't tested it. Oh, hold on. There we go. See, and it it parses a struct right here. And what this allows you to do basically is it, for instance, allows you to define types or even functions while you're creating a function, right? So here we're defining a function, we p global, and we create a struct. during the this, right? So this is an example of part of the advantage of metaprogramming. And then built-in Sterling, I hope I don't need to explain this. This is just a path to get the C function Sterling. Now you'll notice a whole lot of these functions are just C functions that have been forwarded, like a gets, puts, well, gets, I mean, is, it doesn't actually call the, gets function. What it does is it reads in a certain number of characters, right? And it'll read that many characters. It actually doesn't tell you how many characters were actually read. So, I guess that's kind of a problem. Maybe I need to fix this. But, thinking about it, this is a pretty poorly written function. But okay, back to the point. I'll fix that later. Back to the point, a whole lot of these are basically just C functions that have been forwarded to Coder's Basilisk at compile time. The reason for that is that compile time Coder's Basilisk is really slow. The interpreter I wrote for it is quite poorly written. I do need to go in and actually write a bytecode interpreter for it or something, because right now it's a tree walk interpreter. It literally executes the AST directly. I do have a compressed version of the AST that it actually executes, but that's still not a whole lot better. So it needs to be changed at some point. Although it does work. It's just that it's slow. By slow, I mean like maybe 100 times slower, maybe 1,000, a lot slower than native code, right? So anyway, this is the list of built-in functions. A lot of these are accessing the state of the parser, like get next, peek, etc. That's fairly obvious. Get AST, this allows you to access the AST. This one is pretty interesting. Let me show you that. So what this does is it gets a whole bunch of it gets the address of a whole bunch of variables that are part of the parser, and then that are part of the compiler, I should say, and then shoves them into a struct, and then returns the address of that struct, right? So this is the built-in AST, right? Pass AST, right? And then it gives you, it's full of these pointers, and it returns a pointer to this object here. Thinking about it, I don't actually need to have ret val here. I could just write and passed AST all these times. Whatever, right? The GCC is smart enough to optimize this, right? Yeah, but anyway, so this is a little bit of Codegen Code, So that's the main thing I wanted to talk about today is Codegen Code, the basics of how parse hooks work, right? Hopefully this is fairly obvious. A Codegen function starting with parse hook underscore can be invoked at, and then this stuff right here. So at QQQ calls this thing, right? And we demonstrate that here. I'm slightly disappointed I wasn't able to put it here, right? Does it seriously require me to? Yeah, it does. It does. So these are the places in an expression where you can put parse hook calls. I might extend this later, but that might actually be kind of complicated. This is probably good enough, right? Anywhere that you can have a new expression node, but not an operator, it seems to work, right? Okay, so this is me using I'm using some built-in functions. I'm accessing the argc and argv, and this is a good example, right? So I'm gonna first of all let me commit this to GitHub. Oh, that's stupid. Branch-m main initial. Okay, let's make a repository. I know that this tutorial episode has been a bit rambly. To be honest, it's my style to ramble about the compiler when I'm trying to explain it. You're just gonna have to roll with the punches. Create a repository. So let's git add origin, git add codecode.org, gex / this name here. Let's push dash u origin name. Oh, git, not gut. There we go. And now it should be pushed to, yeah, okay. So this is, now you have access to this. This should be in the video description. But anyway, another thing I wanted to talk to you today about was I wanted to talk about the set of available operators that you have available to you. First of all, you should be familiar with the types of statements, right? The only type of statement I believe I haven't explained these two statements, the tail statement and the ASM statement. So I'll quickly demonstrate those. So first of all, let's make a codegen function. myfunc returns A and B, returns an I64, let's say. And let's tail myfunc2, okay? Function codegen. Now, myfunc2 has to have the same prototype. So what we're going to do is we're going to take this and just call it myfunc2, right? If you tail call another function, it must have an identical prototype. And basically what this does is it is a way to optimize tail calls. If you're going to tail call another function, right, as in it, you're just going to jump into it. Tail allows you to do that, and we're going to return A plus B times B, whatever, right, and then we should call this somewhere. Let's actually use buff. Now we're gonna built-in puts. Let's actually have another one of these here, and then we're going to call myfunc, and we're going to print its value. So built-in I to A, buff, comma, myfunc of 3, comma, -5. Right, so we're going to have -5, comma 3, right? Because we want it to be a negative number, because that's interesting. Built-in puts, buff. That should work. I believe that's... see, and now it's 4, right? So what it's done is it's taken -5 is A, and then plus 3 times 3, which is 9, which actually is not a negative number. So let's make this -100, -91. There. Right. So -100 plus 9 is -91, right? And so here's that value, right? We're using built-in I to A to convert the integer to a string, which gets written into buff, and then buff gets printed. Right, so this is an example of using another built-in function. But anyway, this is how you use the tail call statement, and then the asm statement. Basically, what this does is it just inserts some code. It basically is just a way to have a bunch of text, which should get literally written to the output file. Now I could actually write some code here to grab the AST, grab this symbol, and then and then walk through this list of statements to grab the text of this asm statement. But you're just going to have to trust me. This literal text is contained inside of the AST of this function. Hold on, I didn't actually want to do get AP there. I wanted to do this, right? So now this string here, this string, a bunch of text, which should literally get written to the output file, is in the AST of some function, and it is listed as an asm statement, right? So that's the asm statement. The inline C utility that I showed you in one or more of the previous tutorials, secretly the way that it works underneath is it just creates one of these, and then the asm statement by the C code. Actually, I can show you. Slash library 2C. What it does is it basically just takes the text This is where the text is stored in that node, right? This, I know this isn't exactly named that way, but it's that's what it's being used for here. And it just says that this is the text for the statement, right? The text for this statement is this text, right? So this text will be literally written into the C code. I could show you this in action, but I think it's pretty obvious. I don't need to explain it. So basically, in the spot where this statement is compiled, it's literally going to insert this statement. And similarly, for the TP-CPU backend, it literally writes this as the output file. And of course, by the way, it's up to you to actually implement that behavior. So with this code generator here, we don't actually generate any code, so this does not actually get written to any files. It's just, if there was a backend, the backend should be programmed such that this code here gets literally written to the output file with minimal interpretation, right? You might, for instance, have some way of referencing local variables or something, which is, by the way, is why inline C exists, so that you can reference local variables. But anyway, so that's this is the basics of Codegen Code. But also, I wanted to talk about other things, right? So, for instance, Codegen Basilisk has some operators that that C does not, right? Notably, it has the strec and strnic. Operators, right? So we're comparing two strings here. So make these longer. Right, so now these two are equal. We can also do strnec. That's another operator. See here, these are not equal, right? Not equal in a different way produces 1, and then equal produces 1 for this operator, right? So strec means two strings are equal, and strnec means two strings are not equal, right? So basically, Codegen Basilisk has some special operators for comparing C strings. Now, notably, the way that strec works in Codegen Code is that it just calls a built-in implementation of strec. But in order for it to work on a compiled target, you need to define a function impulse strec, right? And I believe the best way I can explain this is I can go to, hold on, not here. Let's close these. Let's go through that. I can show you the one for here is the implementation of impulse strec for the 2C code generator in the user mode standard library. It needs to be defined as pure, as I recall. Inline is optional, I think, but actually I'm not sure. It might be required that it be defined inline. But this function here is basically the function. This function must exist if non-Codegen code uses the strec operator or strnec. If this function is not defined, then strec and strnec are off limits. And the reason that I have it made this way is so that code generators can always assume that there is an implementation of strec that it can fall back to, right? So, for instance, it can you don't have to implement strec in your code generator. You can just implement a call to this function, and that's why I wrote it that way. So keep that in mind. Another thing that Codegen Basilisk has that that C does not is the signed shift right, right? So what this does is it's basically the same thing as shift right, but it's arithmetic. Right? If we do this, this will produce a very different answer. See, if I do this, right, this has an entirely different meaning than this, and that's because signed shift right, arithmetic shift right, schra, as I call it, shift right arithmetic. I believe that's literally what it's called in the AST. So we can check. It's ARSH actually. X for ARSH. That's this, right? This is the reflection library for Coder's Basilisk. But anyway, so this right here will preserve the sign bit, right? So I can change this. If I change this to a positive number, it'll be the same for either one. Right, so because arithmetic sign shift means the same thing as logical right shift if the number is not negative. All right, so there's this. Right. And then if I make it negative 47, and if I do this, huge number, right? So that's something that Coder's Basilisk has that C does not. Also, by the way, I should note that all bit operations automatically promote to the target's word size, right? Oh yes, and another thing I should mention about Coder's Basilisk, and this is one of Coder's Basilisk's big limitations, is that it is basically required that the word size of the machine you're working on, right, the size of a pointer, let's say, right, is the largest possible type that you want to work with, right, that you want to meaningfully work with. For instance, if you're on a 64-bit platform, the largest size of a primitive will be 64 bits. You're not going to have any 128-bit integers or floats or 80-bit floats, which is not true on x64. This is a limitation of Coder's Basilisk in and of itself. You can work around it by creating your own AST in your own language that sits next to the base level Coder's Basilisk. You can also get around it by using inline assembly, right? You can write code which works with 128-bit integers in assembly here. But Coder's Basilisk itself, the base level language here, cannot ever know about a 128-bit integer or something like that. Similarly, if you're compiling for a 32-bit target and you want to access 64-bit integers, bit shift operations and whatnot are not going to work properly because they're always going to promote to a 32-bit. They're always going to convert to 32-bit. It's not going to work very well. So that's something to keep in mind with Coder's Basilisk. Coder's Basilisk kind of requires its base level language to be working with the largest primitive be the word size, right? So that's important to remember. Another thing that I think I failed to show you, let me see if I've forgotten anything. These should be false sign. Is the move operator. So basically, right, imagine for a moment that I have 2 pointers. Int pointer AP, int pointer BP, right? So these are, and I assign A equal to 3 and B equal to 5, right? Now, what you can do is you can do AP, let's actually, Codegen, A equals 3, B equals 5, AP equals get global PTR, okay. Oh, by the way, I should mention, there is no way to get the address of a local variable. You can only get the address of a global variable, right? And this is how you do it. BP of B. Now what I can do is I can do AP colon equals BP. And what this is going to do is it's going to assign the value of B to A, right? So if I do a printout right here of A, it should print out the value 5, at least if I'm remembering how it works correctly. Just in a semicolon. So you see here, see now A has the value 5 because, and so basically what this is doing here is AP is a pointer to A, BP is a pointer to B, and what we're doing is we're saying copy the memory pointed to by BP to the target AP, right? This is the destination, this is the source. So this is the mem copy operator. And I realize that this may be not the most intuitive symbol to use for this. Many programming languages use this for like define a variable or something. But in Coder's Basilisk, this is the memcopy operator. I call it the move operator. Because what it does is it literally mem copies, right? Which is what moving in C++ does. If you move an object from one variable to another, you're not doing a full deep copy. You're literally copying the value of the top level struct from one place to another. And so that's how that works. Anyway, so I think that's most of what I want to talk about here. There's not much more that I want to cover this episode, but basically all you need to really understand this episode is that this is how parsehooks work right here. Here's an example of parsehooks being used. Here's the tail call statement. This is the asm statement. Here's the move operator. Here's global PTR. There's another thing like this. Get fn PTR, which gets a function pointer. The way function pointers work from Coder's Basilisk, get fn PTR and call fn PTR. The way that function pointers work in Coder's Basilisk is that they are not in the type system. You just get a byte pointer, and then you have to pass it a prototype function. I'll explain how this works in another episode. Here are some built-in functions being used. Notably, this right here, this is something you need to pay special attention to. This is calling the parser again. This is Codegen main. This is a Coder's Basilisk program which does not use any libraries, right? So this is entirely self-contained. The only thing you need to be able to know in order to understand this is the language itself, right? This is all stuff that's in the base level language. I know that my style of explaining here probably wasn't all the best. It was probably fairly confusing at times, and I went on lots of little tangents and stuff, and my voice is probably getting annoying. But, this is the episode, and I hope you guys enjoyed. Thanks for watching.